Good afternoon, everyone. Welcome back to E304. So in the last lecture, we reviewed a little bit about atoms and electrons and energy states. So let's just a quick recap. If we have a single atom, the electrons in that atom have discrete energy states. Discrete energy states. Okay, if we have many atoms together forming a solid, a bulk solid, so many atoms together, then those electrons begin organizing in energy bands. Okay, so today we're going to start talking about how we determine how those electrons that exist in the various energy bands, how many of them are useful for conduction of current or heat. So which electrons are available to conduct electricity? And that's the question we're going to try to answer today. So let's look at the Fermi energy first. So let's assume that we are at 0 Kelvin. Okay, that's a very important assumption here. So the Fermi energy here is the probability of finding an electron at an energy level E. Okay. So all the energy levels below the Fermi energy are filled at T is equal to 0. Okay, so the probability is 100% or 1 that you will find all of the electrons below that Fermi energy level. Okay, and that's at T is equal to 0. So that's what F of E tells us. It's a probability of finding an electron. Okay. And at T is equal to 0, the entire probability is that the electron will be below EF. Okay, well, if we increase the temperature, to something above 0, absolute 0, well, then we see that extra thermal energy in the system causes some of our electrons to have some probability of existing above E sub F. Okay? So the electrons jump to that conduction band, and the F of E decreases in the valence band and increases in the conduction band. You can see even in insulators, even when we have this huge band gap, there's some probability, some small probability, that some of those electrons will be in the conduction band. And of course, these are the electrons of interest. These are the electrons that conduct heat and current for us. So these are the ones that we're concerned with. Okay, so what is the total number of those? How many can we have? So let's see. This is where we start getting into a little bit of math. And we're going to start off with one equation that I'm going to ask you to trust me on, and then we're going to sort of derive everything else from here. All right, so here on the left-hand side we see energy. Energy is going up in this direction. We have a number of filled bands, so these are the electrons that are in those 1s, 2s, 3s orbitals that are completely filled. Of course, remember the valence band is the last band that is filled. It could be partially filled. And then the conduction band is the first empty band. All right. So the total number of electron energy states that are available to be filled up to some arbitrary energy level E is equal to E naught, so somewhere in the valence band here. So the total number of electron energy states that are available is given by this equation here. So I'm going to ask you to trust me that this is an accurate equation. Okay. So this is a total number of available states. Then the concentration, or number of states per unit volume, we can get that by dividing n sub s by the volume. Okay, and then we get a concentration. So little n denotes concentration of states. Okay, so these are the concentration of states available up to a certain energy level. If we take that concentration of states, and when we want to really look at a small delta E segment of energy, so we take the little n sub s, and we take the derivative with respect to energy E, or the small delta E, then that gives us the density of states. So this is states per unit volume per unit energy. Okay, so per unit volume because we divided by the volume, and then per unit energy, we just took the derivative with respect to energy. So if we think back on the electronic configuration of an atom, we might remember that the number of states that exist at higher sublevels is getting higher. So there's more available energy levels in higher bands. So that should make sense if we think of how energy levels are filled in an atom. So one way to, this per unit volume per unit energy thing is a little bit confusing. So let's think about it in terms of an analogy. So this is density of electron energy states. Think of it as an apartment building. And on the first story of your apartment building, you might have 4 apartments. Okay, so you have 4 apartments, and let's say the volume of the building is 100 meters cubed. Then your density of apartments per story per meter cubed is 0.04 apartments per story per meter cubed. All right, well, if on the second story you have then 8 apartments, then your density of apartments, or density of states for that story, is going to be 0.08 apartments per story per meter cubed, and so on and so forth. And you can see that there's it becomes more and more dense. There's more and more apartments in that same volume, okay, or in that same size of story per meter cubed. So you can sort of use this analogy to understand the density of states. So again, density of states is per unit volume per unit energy. Okay. Now, we saw that we have some available states, and density of states gives us that. But just because there is an available state, what's the probability that an electron is actually filling that state? So that's the next question. So in order to find the density of actual electrons, not just available states, we have to consider both. We have to consider the availability of a state and the probability that an electron is actually filling that state. So we multiply them. So the ds of E is the density of states, and multiply that by the probability of having that state be filled. Okay, so we multiply those equations together, and this is what we come up with. And I encourage you in your notes to please go through and make sure that you can do these calculations, starting with, let me skip back real fast, starting with n sub s. Like I said, please trust me about this equation, but you should be able to divide by volume and achieve the little n sub s equation, and then you should be able to take the derivative of that with respect to energy and get the density of states equation, which is this one here. And then from that, we can take the density of states equation and multiply it by the Fermi, the probability equation here, and achieve this. All right. So the electron density the electron density per unit volume. Okay, we take and we integrate from 0 to infinity this equation, the probability times the density of states. Integrate from 0 to infinity with respect to E, and that gives us our total electron density. So we're getting rid of the per unit energy part of it. Then at temperature is equal to 0 Kelvin, we know that that probability is always 1, that the electron will exist at some EF less than, some E less than the Fermi energy. And this is for a conductor. Okay, so the example of a conductor. So if we can take this f of E and set that to 1, because we know the probability will always be 1, and we integrate from 0 to EF, again for a conductor, f of E becomes 1, so then we're just integrating the density of states from 0 to EF. Okay, well, if we take that integral, and again I encourage you to on your own paper see if you can achieve the same result, then N sub E, the electron concentration, okay, N sub E, the electron concentration, becomes equal to this expression, which is, these are all constants. H is of course a constant, M is mass, so EF is really the only a variable. So if we solve for EF in the above equation, we see that the Fermi energy, EF, is solely dependent upon the electron concentration, and this is a fairly important result for us. Everything else is constant, right? Mass is constant, H is constant, so the Fermi energy is determined solely by the electron concentration. And this is again in a conductor. So let's see some examples. So here in this table we can see some examples of metals or conductors at temperature of 300 Kelvin and electron densities, electrons per meter cubed, so this Ne given here, and the Fermi energy levels given here. So these are in your book for your reference. Now, what happens in the case of a semiconductor? Well, in a semiconductor, we know that there's a separation between the valence band and the conduction band. So let's take as a point of reference the bottom of the conduction band and the top of the valence band as our energy references, right? So the equations for density of states in the conduction band and density of states in the valence band are very similar to the ones in a conductor. The only difference is that instead of just E, we have to account for the fact that there's a separation between EC and EV. Okay, so E is replaced by E minus the bottom of the conduction band energy, or the bottom of the valence band energy minus E. So we're accounting for the fact that there's a gap between the valence and conduction bands when we're doing those calculations. So keep in mind, if we're talking about a semiconductor, the equations become just a little bit different than if it's a conductor. Okay, so if we look at electron concentrations, again, this is our valence band. We have some band gap, and then the Fermi energy is going to be somewhere inside this band gap. Okay, and then the conduction band is up here, so we can see that in this particular case we have some electrons that are sitting in the conduction band and some holes or absence of electrons in the valence band. Okay, where some of these electrons have hopped up to the conduction band from the valence band. So let's look at the effect of temperature on this in a semiconductor. So here we are in a semiconductor. Okay, so conduction band up here, valence band, let me use a different color so you can see better. Conduction band, the bottom of the conduction band is up here, the top of the valence band is up here, the Fermi level is somewhere in between. Okay, Now at 0 Kelvin, at absolute zero, none of these valence band electrons have the energy to jump up to the conduction band, okay? And they can't exist in the band gap. That's not allowed. They have to be either in the valence band or in the conduction band. Since none can be as high as the conduction band, then we know that everything exists in the valence band. As we increase temperature, so we're increasing temperature. Okay, so at higher temperatures, we can see that some electrons begin to reach the conduction band. So our Fermi energy is becomes this distribution here. So you might remember, I hope you remember from the first plot we had, we saw that at 0 Kelvin, the probability distribution looked something like this, and then as temperature increased, your probability distribution begins to look something like this, where there's some greater probability of electrons existing in the conduction band. So we can see that there's some probability now that an electron can jump the entire band gap and then exist up here in the conduction band. Okay, so if you get high enough energy, some electrons have energy above the Fermi level, and they can exist up there.